Voilà.
Okay, so hello everyone. Today we have the pleasure to listen to Kevin Balc'h, who is a colleague in Bordeaux, even if we are not in Bordeaux these days. Okay, so we will talk about exponential bounds for gradient of solutions to linear elliptic and parabolic equations. Well, thank you all for being here, and please turn off your microphone during the talk. Thank you.
Okay, so thank you, Sylvain. And also, I would like to thank all the organizers for giving me the opportunity to present my works today. So today I will focus on one work concerning exponential bounds for solutions to linear elliptic and parabolic equations. And the plan of the talk will be the following one. So first, I will begin by introducing, let's say, two main motivations about the main results that I will present after. So actually, here there are two strongly connected subjects. And I will then devote some time to prove the main result of the talk, that is to say gradient estimates for solution to linear elliptic and parabolic equation. And then I will finish by some application and some possible extensions to these gradient estimates. So let us begin by the Landis conjecture. So the story begins in 1960s, where Landis made this following conjecture. So take a bounded potential in Rn and take U a solution of this elliptic equation in Rn and assume that U decays more than exponentially. Then Landis made the conjecture that U necessarily equals to 0. And this is motivated by the trivial observation that you can indeed construct exponential decaying solution, at least far from 0. And it seems at first glance that you cannot expect to decay more than exponentially if you satisfy this type of elliptic equation. But more than 20 years after, Meshkov brought a very striking counterexample to this conjecture, because he constructed a potential V, complex valued, and U, also complex valued, satisfying this elliptic equation in a plane with U decaying like exponential minus x to the power 4 over 3. So 4 over 3 is bigger than 1, so this is a negative answer to the conjecture. And he also proved that 4 over 3 is actually the good exponent, because he proves that if you take a bounded V and U a solution of the elliptic equation with U decaying more than exponential minus x to the power 4 over 3, then U necessarily equal to 0. So this could be the end of the story, but actually no, because in 2005, Koenig and Bourgain reformulate the Landis conjecture as follows. Actually, this is motivated by the fact that in the Meshkov counterexample is complex valued. So they reformulated the question as follows. Is the Landis conjecture true for real valued potential? So now take a bounded potential real valued and assume that U decays more than exponentially. Can we prove that U necessarily equals to 0? And they also proposed what is now called the quantitative Landis conjecture, which states something like this. So take V bounded by 1, real valued, and U also bounded by 1, satisfying also the elliptic equation with U non-trivial. Can we prove that for every R sufficiently large and for every x naught of size R, can we prove that we can estimate the supremum of U near x naught by an exponential like this? So a positive answer to this quantitative unique continuation result will actually give a positive answer to the Landis conjecture for real valued potential. And there are many recent results about the Landis conjecture, and I will speak a little bit about some of them. So for this conjecture, there are, for instance, Rossi result in very recently who proved the conjecture for general elliptic operators in dimension 1, or when U is radial, or when the elliptic operator is radial, or when the solution is non-negative, or when the generalized principal eigenvalue of the operator is non-negative. And very recently also, Sirakov and Souple extended to the case of unbounding coefficients. And concerning quantitative Landis conjecture, which is this conjecture, there is this pioneer work by Koenig, Silvestre, and Wang in 2015, who proved the result for a potential V non-negative in the plane R2 using conformal mappings and Twist-Fair theorems. And this has been extended by these guys also. And also very recently, Logunov, Malinikova, Nadirashvili, and Nazarov extended this result for potential V allowed to take negative values, also in the plane R2. So after this discussion, I want to convince you that this conjecture is actually strongly linked to observability estimate that we use to manipulate in control theory. So now take omega, a bounded domain in Rn, and take phi, a solution of this elliptic equation with homogeneous Dirichlet boundary condition. And we know from Kahneman estimate that you can observe phi in big omega by phi in little omega with an observability constant of this form. And this observability constant actually appears when you are performing Kahneman estimate. It is linked to the Kahneman parameters that appears. And we may wonder if this is sharp in the sense of if this constant is optimal in function of the potential V. And actually the answer is yes. This is optimal if you consider complex valued potential and complex function satisfying this elliptic equation. In fact, by using Meshkov counterexample, if you forget the boundary, it's not very difficult to construct a solution of this elliptic equation, decaying very fast in the interior of little omega, decaying like this, with a size of potential R square, so you cannot decrease the 2/3 here. And a natural open question that appear is, can we replace the V 2/3 by V 1/2 if we consider real valued potential? And we know that the answer is yes in dimension 1, or for V constant, or for 2D manifolds without boundary, by using the very recent result by Logunov and its collaborators with a logarithm loss in the potential V here, but and the same open question appear for parabolic equation. So now let's take phi, a solution of this backward parabolic equation. And we know from Fermo-Descartes-Loiseau in 2000 that you have this kind of observability estimate, that is to say phi at time 0 can be observed in big omega by phi in the small cylinder 0t times little omega with an observability constant of this form. We mark that the V 2/3 also appear, of course. And we may wonder if this optimality constant is sharp or not. And this is the case if you consider complex valued potential, also by using Meshkov counterexample. And we may wonder if we can replace V 2/3 by V 1/2 if you consider real valued potential. And we know that this is the case in dimension 1 by using transmutation method. And we also know that this is the case for non-negative initial data and for real valued potentials. So after this, this introduction and the main motivation of the talk, let's present the main question and the main result of the talk. So when I started to study Landis conjecture, my previous PhD advisor gave me this following proof of the Landis conjecture in the one-dimensional case. So if you take U a solution of this elliptic equation in the real line, and if you assume that U decays more than exponentially, and you want to prove that U necessarily equals to 0. So if you integrate this equation, it's not very difficult to prove that the derivative of U also decay more than exponentially. So now if you define phi, the solution of this second order differential equation with 0 data, you can use Grunwald estimate to obtain that phi and phi prime grow at most exponentially. So now if you multiply the equation satisfying by U by phi, and if you integrate by parts, you only have, you have the integral between minus r and plus r of the absolute value of U is equal to only the boundary terms here. And by using the fact that phi and phi prime grow at most exponentially and U prime decay more than exponentially, you find this type of bound. So sending r to plus infinity, you necessarily have the fact that U is equal to 0. So when I saw this proof, I asked myself this question: if we can extend this proof to the multidimensional case, because here the proof is very one-dimensional because we see the elliptic equation as an evolution equation of second order. So here's the main question of the talk. Can we extend exponential bounds for solutions to elliptic equation and parabolic equation in the multidimensional case? And actually, the answer is yes, in the following sense, or for reasonable elliptic equation. So here's the main result. Take W, a vector valued function, which is bounded, and V, a non-negative bounded potential, and F, a bounded source term. So if you consider this elliptic equation with source term F and with homogeneous Dirichlet boundary condition, then you can prove that the gradient of phi is estimated by this exponential times the L infinity norm of the source term. So to reformulate, we have the fact that the gradient of phi grows at most exponentially in function of the diameter of omega, where omega is the set where the equation is posed. And you can also explicit the constants that appear here. So let's do a couple of remarks about this theorem. So actually, we already know that there exists a positive constant C such that you can estimate phi in W1 infinity by C times the L infinity norm of F. Indeed, by using maximal regularity in LP for P sufficiently large and Sobolev embeddings, you obtain this, and if we plug this together, you obtain exactly this. So the main contribution of the theorem is to make the things, or to make the constant at least more explicit in function of the parameters, that is to say in function of omega and in function of W and V. And we can discuss after the optimality of this constant. And the same works for parabolic equation, essentially. So take now W as before and V also as before, but now V is allowed to take negative values if you want. And if you take a source term bounded in a parabolic cylinder, and if you take phi naught smooth data, so if you take phi a solution of your parabolic equation with homogeneous Dirichlet boundary condition, then you can prove that the gradient of phi is bounded by this exponential times the initial data in a sufficiently smooth space plus the source term in L infinity. So let us remark that this term is exactly the same that appear in the elliptic case. And this term directly comes from the dissipation of the operator dt phi plus v phi. Okay, So now let's do the proof of the main result. And actually, I will only do the proof of the elliptic theorem, which is the following one. Okay, so first we will reduce to the case V is equal to 0 and omega is the ball of radius r centered at 0. So we have this elliptic equation. So now we have no V. And our goal is to simply prove that the gradient of phi grows at most exponentially in function of r. So we will follow Andrew's Clutterbuck argument, and I will explain basically the idea. So when you have a solution of an elliptic equation, here it is phi, then the modulus of continuity of phi is also a solution to another elliptic equation. So now you can apply maximum principle for this new elliptic equation to deduce bounds on the modulus of continuity of phi. So by coming back to the variable phi, to deduce bound on the gradient of phi. So this is mainly the idea. So this is why we introduce z, which depend on x and y, which is equal to the modulus of continuity of phi minus theta, a function of one variable that depend on the distance between y and x. And theta is chosen such that theta satisfies this second order differential equation, where here the parameter are chosen such that theta prime stays strictly positive in 0R. This will be used after. So now the crucial remark is the following one. If you manage to prove that z is non-positive, then you deduce a bound on the modulus of continuity. Then by using the fact that theta naught is equal to 0, you immediately deduce a bound on the gradient of phi by theta prime of 0, which is equal to what we want. So now, perhaps the most technical slide, but one of the most important also. So I will go quite slowly. So I repeat, we have phi, the solution of this elliptic equation, and we have defined theta, the solution of this second order differential equation, and we have introduced this quantity. And our goal is to prove that z stays non-positive to obtain the result. So by using the fact that z is continuous on the compact set omega bar times omega bar, we know that z attain its maximum at x naught, y naught, at x naught, y naught. So if x naught is equal to y naught, we have 1, because if you plug this in the definition of z, we immediately obtain that z stays non-positive. So this is okay for this case. So now let's assume that x naught is different from y naught. And if x naught or y naught are on the boundary, I will not develop, but you can obtain a contradiction in this case. It is not possible. So let us focus now on the generic case x naught different from y naught and x naught, y naught are in the interior of omega. So now you can use your optimality condition because x naught, y naught is the maximum. So you can use that the gradient of z is equal to 0 and the Hessian of z is non-positive. So this is what we will use here, but we will use in a clever way, let's say, in a way due to Andrews and Clutterbuck. In fact, we can choose an orthonormal basis EI such that the last vector is proportional to y naught minus x naught. And we will use the fact that the gradient of z is equal to 0 to obtain this equality for the gradient of phi at y naught and the gradient of phi at x naught. And we will derive 2 times this quantity, which have to be non-positive because x naught, y naught is a maximum. And here we remark if we compute this second derivative along this path, the distance between y and x is always equal to 1 minus 2s. So if you derive this quantity 2 times with respect to s, this term will become minus 2 times the second derivative of theta, which have to be non-positive. And along this path, the distance between y and x is constant. So if you derive this quantity with respect to s, you obtain 0. So you obtain that this quantity has to be non-positive. And you do this for I between 1 to n minus 1. So now, you sum these n inequalities and you recover the Laplacian of phi minus the Laplacian of phi minus 2 times the second derivative of theta. And now you use your elliptic equation satisfied by phi to give a lower bound of this term by this term. And you finally use the elliptic equation satisfied by theta to obtain that this term is strictly positive. So you also obtain a contradiction. So you obtain that the maximum is only attained on the diagonal of omega bar times omega bar. So this concludes the proof. So I really want to insist on the fact that if you do the more natural thing that consists on computing the Laplacian of z, and to see the elliptic equations that appear, then you cannot obtain the result, at least in the multidimensional case. You really have to use mixed derivative of z to conclude. And this is hidden here when I am computing some optimality condition for particular direction. Okay. So now I explain how we can reduce the case v non-negative to the case v is equal to 0. So this is based on the following lemma, which states the existence of a positive multiplier to the homogeneous elliptic equation satisfying precise, let's say, estimates. Indeed, let us admit the lemma for the moment. So if we have this solution of the previous elliptic equation, and if we define phi hat, which is equal to phi divided by psi, now the new variable phi hat satisfies this elliptic equation with no v. We have killed v, but we have changed, of course, the potential w, which is now w hat. And by using the previous case, we have an estimate of the gradient of phi hat, which is smaller than this exponential, And by using the precise estimate that we have on the multiplier, it's not very difficult to deduce the bound that we want. So let us say a couple of words about the existence of this positive multiplier. So here we use the fact that v is non-negative to construct a solution of this equation. So indeed, it's not difficult, let's say, to find subsolution on supersolution to this equation with the subsolution smaller than the supersolution. So you can immediately deduce the existence of a solution of this equation, which satisfy the bound that we want. And by using now interior regularity estimate on Harnack inequalities, using the fact that psi is strictly positive, you can deduce this bound of the gradient of the logarithm of psi, which is crucial to obtain this bound here. Okay, so now let us give some application of the gradient estimate, let's say. So take W bounded vector valued function and V bounded potential, non-negative also, and take U a solution of this elliptic equation in Rn. Then you can prove that U in the ball of size R is smaller than U in the annulus X between R and 2R with a constant of this form, a constant exponential of R mainly. So in particular, this gives a proof of the Landis conjecture for this particular case of elliptic operators, because if this term, if you decay more than exponentially, this K will decay more than exponentially in function of R, so this term will go to 0 as R goes to plus infinity. So how to prove this is, this was already, concerning the Landis conjecture, this was already known by Rossi for this particular case of elliptic operator. So it's important to mention it. So how to prove this type of estimate? So this is based on the duality argument that we present in the one-dimensional case. You have U, the solution of this elliptic equation, And if we define phi r, the solution of the adjoint elliptic equation with a source term equal to the sine of u, with homogeneous Dirichlet boundary condition, by using the gradient estimate that you have on phi r, we have this. And by introducing now a cutoff function, which is equal to 1 in a ball of radius r centered at 0, you can multiply your equation satisfying by u by the cutoff times phi r, and then you perform integrate by parts, and you find this kind of estimate for this integral. And by using the gradient estimate that we have proved before, we exactly prove what we want. But this seems to be not very optimal because at least at least in function of v, I would say, because you can actually prove by another method this type of bound. If you take u a solution of the same elliptic equation, then you can estimate u in the ball of size r by u in the sphere of radius r with an exponential that does not depend on v. So this seems to be not optimal in function of v because here v is non-negative. So what is the conclusion of the talk in a few words? So I have spoken about two strongly connected subjects, the Landis conjecture and observability estimates, which have motivated, I would say, this work about the proof of exponential bounds for gradient of solution to linear elliptic and also to parabolic equation. And this also leads to estimate like this for adjoint elliptic equation based on the duality argument in the one-dimensional case. So possible extension for the future, I would say. We can also consider other boundary conditions for gradient estimate. So I have some partial result for homogeneous domain boundary case. We can also consider time-dependent coefficient in the parabolic equation. We may also wonder the optimality of the constants that appear in function of v. And we may also consider more general potential v in quantum confidence, and we can generalize this result. So thank you very much. That's it.
Well, thank you.
Thank you.
So yeah, as usual, I'm the only one to applause, but so there are some people putting the hands in the pictures. Okay, so thank you very much, Kevin. Is there any question?
Yes, I have a question.
Thank
you for your talk. My question is about the domain omega. You explain your gradient estimates for a general domain for the ball. But for a general domain omega, do you need some convexity assumption or smoothness assumption on omega?
Yes, sorry. Yes, I have forgotten to mention, but we have to assume that the domain omega is smooth and it is convex also.
Sure. Okay. Thank you.
Okay. Is there any other question?
Yes.
Yeah.
A similar question to the previous one. Is it necessary the diameter of omega what appears there? Is there? Have you explored another characteristic of the domain apart from the diameter that have an influence in the estimate?
Sorry, I have not understood the question. So sorry.
Yeah.
So you want to perhaps you want to avoid this term and to introduce another function of omega.
Yes.
Yes. To be perfectly honest, I have not very thought about, so I have not very clever answer to this. Sorry.
Okay. Okay.
But perhaps we can use other function of omega. I don't know.
Yes, because in the case in which you, in the estimates that you have considered before, where there were a small domain omega where you are trying to obtain the observability estimates,
Yes.
it is not the diameter of the omega, it's something more, there is more subtlety there in
Yes, okay, I understand.
geometric. So I wonder if is there another possibility of taking into account the properties, the geometrical properties of omega there?
Yes, yes, perhaps. Yes, I don't know how to proceed. Yes, but yes, perhaps.
Okay, okay. So I think
Emmanuel is raising.
Yeah, he's raising his hand. He's very polite.
Can you generalize to more general elliptic operators? I mean, here you gave result on the classical Laplacian, but can you generalize your result to more general elliptic operators?
Yes, yes, I think we can. Yes, I think we can. Let's say we can take a diffusion which is not equal to 1, of course, in front of the Laplacian. But for let's say diffusion that depend on space, yes, no, it's not sure that we can do it very easily, because here we really compare the solution of the elliptic equation in the multidimensional case to some elliptic equation in the one-dimensional case. But yes, perhaps we can also by introducing a coefficient here that depend on the diffusion that we take here. It is possible, I believe. Yes, it is possible. I'm not sure that I'm clear, but yes, I think we can.
Yeah, okay, thank you. The key point is there. Yeah.
Okay, is there any question? Well, I have one, in fact. So regarding your construction, it seems that so you consider first order terms.
Yes.
Sometimes it is W gradient of U, and
Yes.
some other times it is the divergence of W U.
Yes.
Principle, those two terms should have the same kind of difficulties, right? And despite that, it seems that some of your results concern W gradient of U, and some others, and the other one are consider divergence of WU. So could you be able to handle both simultaneously?
No. No, because actually here they're really related by the fact that the adjoint of this operator is this one, sorry. And if you try to perform gradient estimate for this one, so yes, I have some trouble yes, this is hidden here. For instance, if you try to compare the solution of this elliptic equation to this one, yes, here I have some trouble to, here I really use this fact, and I use the this optimality condition of the gradient of phi. And if we try to replace this operator by the operator you mentioned, I cannot use this optimality condition to give a lower bound. So I do not manage to get the estimate.
Okay, well, thank you. Are there any other questions? Well, if not, let's thank again Kevin. And well, we'll have 1 or 2 minutes to shift speakers. So next speaker is Jon Asier. And in the meantime, Emmanuel, you have to explain me how you did to raise your hand.
This is my secret.
Okay. Okay. So, Jon?
Okay, wait. Okay, so you can see it, can't you?
Yeah, it's perfect.
Yes, perfect.
Good.
Okay,
So
so you are ready, we can start.
yes, I'm ready. Yes.
Okay. Well, so the next speaker is Jon Asier Barcena-Petisco. He's working in Madrid, if I remember correctly, right?
Yes.
And he will speak about average dynamics and control for heat equations with random diffusion. Well, thank you, Jon.
First of all, I would like to thank the organizer, to thank Sylvain, Enrique, Albert, and Luz for having invited me to give a talk here. What I'm going to present today is a joint work with Enrique Fazua, who is the head of the DICON team and can be found at HAL. Okay, so let me introduce you to the problem. The idea is to study the controllability of the heat equation, but with an unknown diffusion. Here, the coefficient alpha is some unknown, and the only thing that we know is its probability distribution. Ideally, we would like to control the solution for any realization of alpha. That's it. Ideally, we would like to control simultaneously all the realizations. However, this is not possible, which can be seen really easily by considering the case in which alpha goes to 0. Thus, the next realistic target is to see if we can control the average. By controlling the average, we mean either controlling exactly to 0, which could be null average controllability, or getting as close as we want to any given target, which could be average approximate controllability. So these are the two notions of control that we are going to study in this talk. The idea, of course, is that the control F is chosen independently of the exact realization of alpha, and that we control the average. So, as usual, there is an equivalence between the average controllability and some observability notions. In particular, we consider the time reverse tangent system, and we can see easily with the Hilbert uniqueness method that the approximate average controllability is equivalent to a unique continuation property, in particular to the property that says that if the average is null on the observation domain, then the initial value is null. Similarly, the average null controllability is equivalent to an average null observability, which is also a kind of unique continuation, but in a quantified way. It's a usual observability inequality, and the idea is to observe the function at time t at its final value with the mass on the observation domain. So this second property would be equivalent to the null averaged controllability. So what are the previous results? It was proved first by Luan Fazua and then by Kulsunger, Sfari, and Mansouri that given any random variable such that the minimum of all the possible realization is strictly positive, that is that the density is supported in alpha min plus infinite for some alpha min strictly positive, then in that case, the system is null observable in average. They prove it mainly by considering the Fourier decomposition of the solution, and that the average dynamics decay more or less like the heat equation. So they used a Lebor-Roviano iteration method. Now, of course, this result leaves an interesting open question. What happens if the minimum of all the possible realization is null. That is, if we allow 0 to be at the support of the density. Of course, we could consider alpha to be negative, but in that to admit negative values, but in that case, the system is not well posed, which is what justified to focus when alpha is either strictly positive or null. So this is the question that we are going to answer in this talk. What happens if we allow the random variable, the diffusivity, to vanish? Well, in order to illustrate what happened, let us forget outbounded domains and let's take a look at the solutions in the whole domain. Now, in the whole domain, we have the fundamental solutions. So with that, we can operate easily, and in particular, we can compute the average of the Fourier transform of the fundamental solutions. And we get that it is the Laplace transform of rho evaluated in C squared t. Now, this integral can be asymptotically calculated for some density functions, in particular for the ones that you can find there that are functions that decay exponentially to 0. So with those density functions, we obtain that the Laplace transform is more or less exponential of minus c to the 2r tr. The tr already tells us that we are not going to have the semigroup property. In addition, the c to the 2r tell us that the dynamics, that the average of the solution with those density functions, it's going to have a fractional nature. So the dynamics already stop behaving like the heat equation and can acquire a fractional nature. So going back to bounded domain, by considering the Fourier representation, we can see that this is also the case, because in the Fourier representation, we have the Laplace transform of exponential minus of the density evaluated in lambda et, and for the previous density function, this is going to behave like exponential of minus lambda RTR. So in that case, we are also going to have fractional dynamics. Now, the fact that the solution may acquire fractional dynamics already tell us what kind of results we can expect. Now, on the one hand, we should expect unique continuation in average, considering what is known on the fractional heat equation. And in addition, we should have null observability in average if and only if the density function is sufficiently small near 0. By sufficiently small, we have that the threshold is given by exponential, more or less by exponential of minus alpha minus 1, which could correspond to the fractional dynamics of index a half. So if the density function is smaller, we should have the null average controllability, and if it's larger, we should just have unique continuation in average. By smaller and larger, I mean near 0. So, okay, so graphically, we should have, if it's smaller, average null controllability, and larger not. Okay, let us now state the rigorous statement and proof of what Enrique and I prove in that paper. Okay, so first of all, regarding average unique continuation, if the density function is the uniform distribution in 0, 1, or if we have, or if this technical inequality is satisfied, then we are going to have the average unique continuation property. This technical inequality, the objective of this technical inequality is to ensure that if we have two different frequencies, then the one with associated to a larger eigenvalue decay exponentially faster than the other one. So that is what this technical inequality ensures. Also, I would like to remark that the technical inequality is not an empty result, that there are examples, and in particular, we can see that by using the Laplace method, that the function that decay exponentially to 0 at 0 satisfy the given inequality. So how can we prove the unique continuation when the density function is 0, 1? Well, in that case, it is just explicit computations. We can get the solution explicitly, which is 1 divided by t minus inverse Laplacian of rho, plus the solution of the heat equation with initial value inverse Laplacian of rho. So if the function is null on the observation domain, then this expression is null. Its time derivative is null, and its time derivative, it's just the solution of the heat equation. So if the solution of a heat equation is null on observation domain, then the solution is null, and we have the desired unique continuation. Now, how can we prove in the case of the solutions that satisfied the previous inequality, that satisfy that exponential decay? Well, it follows basically from the analyticity of the average dynamics. In fact, the average dynamics are analytic from 0 infinite to L2 of G of the domain, and which is proved in our paper. And thus, when we know that they are analytic, the proof is pretty standard. We have that if the solution is null in 0t time observation domain, by analyticity is null in 0 infinite time observation domain. So if we have such a solution that is null in those domain, then if the initial value is null, we would obtain an eigenfunction of the Laplacian that is null in the observation domain, because different frequency decays exponentially faster, the one with larger eigenvalue than the other. So the one with the frequency with the smallest eigenvalue should be null in the observation domain, but there is no such eigenfunction. So necessarily, if the average is null in the observation domain, then the solution is null. Now, the second result concerns the average null observability properties. Here, again, we have a technical inequality. This technical inequality is necessary to have some exponential decay with respect to the time variable for the solution, and under that hypothesis, we are going to have the null observability in average. Now, that hypothesis is satisfied, for example, for the density function that decay exponentially to 0, but exponentially faster than e minus alpha minus 1. So again, it's not an empty result. And the proof is very similar the proof of this result is very similar to the proof given by Lu and Zuazua, which is based on an iteration method of the type Lebot-Roviano. So, in particular, it's an iteration method on the observability inequality that follows more or less the scheme proposed by Miller in 2010. So also, in fact, the proof for the fractional heat equation almost can be reproduced, except that here we do not have a semigroup property. But since the decay rate is similar, since the previous inequality ensures us some exponential decay with the time variable, we can replicate the proof, so we can prove the result. The final result, this one much more interesting, is that given any domain, given any subdomain strictly contained, if the density function rho if the Laplace transform of the density function is larger than exponential of minus CSR, then the system will not be null observable in average. Again, this hypothesis is a bit technical, but it's not an empty hypothesis. It's satisfied, for instance, by the uniform distribution, by the exponential distribution, by more artificial distribution of type 2 alpha indicatrix of 0, 1, or of function that decay exponentially to 0, but slower than exponential of minus alpha, but minus 1. So the problem is not a lack of unique continuation property. In fact, the problem is that we can find a sequence. Well, it's not a problem of lack of a unique continuation property, because as we have proved before, we have that property, at least for the uniform distribution and for the function that decay exponentially to 0. The problem is the existence of a sequence of initial value such that the mass at time t divided by the mass on the observation domain explodes. So how can we construct such a sequence? To ensure that the mass is small in the observation domain, we need basically two things. One, a geometrical condition, that is that the initial value is supported away of the observation domain. The reason for that is that with that, we ensure that the solutions in the observation domain of any realization for any value of alpha are small, exponentially small at the observation domain. In addition, we also need that the frequencies of eigenvalue smaller than n are null. And that is needed to ensure that at any time, at larger times, sorry, the mass on the observation domain is exponentially small. So as we are going to see, combining both properties, the solution, the average U is going to be exponentially small on the observation domain. Also, to prevent that the average solution from decaying too fast, we need that the solutions are concentrated, that a part of the solutions remains in the first Cn, well, in the frequencies that are smaller than Cn for a sufficiently large C. So the idea is, okay, they are null of the eigenvalues from 0 to n, but a part of the mass of the initial value is concentrated between the eigenvalue n and the eigenvalue Cn. And like that, we are going to ensure that the average solutions does not decay too fast. So as you can see, with the first hypothesis, we obtain that the mass on the observation domain is of the type exponential minus c square root of n. And using the second hypothesis and the Fourier representation, because a part of the solutions it's concentrated in the eigenvalues smaller than Cn, we have that the mass at time t is of the type exponential of minus CNR. And so we can see that since R belongs to 0 between 0 and a half, we have that the limit, that the solutions, that limit explodes to plus infinity. Okay, and how can we construct such a sequence? Well, actually, I'm going to show you how we do it in dimension 2, but the proof is valid for any arbitrary dimension. We consider in dimension 2 a square outside the observation domain, and we divide each segment of the square in C times a square root of n points for a sufficiently large constant C. We do that with each of the segments that allows to construct a grill of size n to d half for the dimension. So, for the dimension. So, with that grill, in each of the points of the grill, we consider a circle. And in each of the circle, we consider a copy of a cutoff function. So, yes, we consider a copy of a cutoff function. So, the proposed solution will be a linear combination of the cutoff functions. And now, we consider the support is outside observation domain by construction, that it's going to be orthogonal to the frequency smaller with eigenvalue smaller than n, just by solving a linear homogeneous system with more equations than variables. And that's the case because of Weyls' law, because Weyls of the law ensures that the eigenvalue is smaller than n are that the quantity of eigenvalue smaller than n are more or less a constant c times n d half. And the third property can be proved by an easy integration by parts and by seeing that the Laplacian grows at most linearly. Finally, I'm going to show you some numerical simulations that we do. In particular, we consider the functional associated to the control problem for fit the average solution of the adjoint heat equation. In particular, we consider the initial value a half. We consider G0P, the domain 0P, the observation domain 1, 2, and we wanted to see what are the differences when we minimize this functional with the uniform distribution in 0, 1 and 1, 2. The reason is that in 0, 1, we do not have null average controllability, and in 1, 2, with the uniform distribution in 1, 2, we do have null average controllability. So, with the uniform distribution in 1, 2, for initial value a half, we see that the minimum of the functional in the first 40, 50, and 63 eigenfunctions more or less is steady. We see a clear sign of convergence, whereas in the case of the uniform distribution in 0, 1, we do not see such a convergence. So, also, we consider we took those controls and put it in the average heat equation to see what happened. And in the case of the uniform distribution in 1, 2, the solution clearly converges to 0. But in the case of uniform distribution in 0, 1, we do not have such a convergence. So, some interesting open problems are the following. To begin with, to study the average controllability of a more general heat equation. In particular, in all the proof, we have used that the explicit solution that the function of the elliptic operator were independent of alpha. But with a more general form, we don't have such independence. So we cannot use the same technique. Other problems include to study the average wave and Schrödinger equations with arbitrary random diffusion. Also to determine how to minimize the variance, which is a very interesting question, because even if we have obtained the control of minimal norm, it would also be interesting to obtain the controls which minimize the variance for the solution. Of course, we cannot make the variance 0 because we do not have the simultaneous controllability. But at least being able to minimize the variance could be very interesting. and also to see if we can have the average unique continuation for all random variables. So I thank you very much for your attention, and I will answer any question that you have gladly.
Well, thank you very much, Jon Asier. So is there any other question? If so, please open your microphone and ask, or if you do not want to use your microphone, you can ask in the chat and I will tell the question. Okay, so maybe I will ask one question. So here you are controlling the average of the solution, right?
Yes.
But so somehow, as you said, you are not controlling the variance. So no. I wonder if it could be relevant, and if you have already seen that, to control the solution and then to control its first order derivative. So you see if the parameters are reduced to a narrow interval, it could make sense simply to control the solution corresponding to, say, the center of the interval, and simply try to further impose that the derivative with respect to this parameter will be 0 at time capital T. Is that something that you have been looking at, that you have already seen? Or?
I haven't tried, but it looks an interesting approach.
Okay. And you never saw this in the literature?
Yes.
Okay.
I'm sure. I can't remember.
Okay, I never saw that as well. But maybe that would be interesting.
I have a question, but I think that it's maybe too technical and maybe it's simple question. You have considered parameter alpha that is affecting the whole Laplacian, but you may also consider different parameters for different directions. I mean, alpha multiplied by the derivative with respect to x1 and beta multiplied by the derivatives.
Yes.
Possible to consider variations of this kind, randomness of this kind too?
Yes, the problem is that we use a lot the Fourier representation for the proof that we used on this paper. So the technique of this, so if we consider some parameter alpha for the diffusion, another parameter beta for the velocity, both of them random.
No. I mean one parameter alpha for each, one different parameter alpha for each direction. X1, X2, alpha 1, alpha 2, for example.
Wait, that looks reasonable. Yes, it makes sense. It all reduces to see if we can get explicit solutions of no. If we can more or less get a Fourier series, then the same techniques are very likely to apply. Please, can we?
Oh, okay. It's just a question. Maybe it's something to compute. Just an easy generalization of the ideas. I don't know. Okay, thank you very much.
Okay.
Okay, thank you. Is there any other question? Well, so if not, let's thank again Jon Asier. Thank you. So thank you to Kevin and John. Thank